Okay, let's read it. A beam AB supports 3 loads. As shown, the material used for the beam has a normal stress sigma equals 1800 psi and a shear stress of 120 psi. Okay, when I say 1800 and 120 psi, this is the maximum stress allowed. Max stress. You should not exceed the stress because something bad will happen. Determine the minimum depth D, so D, such that it meets strength constraints specified by the given stresses. So what is given here is that sigma max is 1800 psi, tau max is 120 psi. Now, this is a classic design problem where you are told to compute D such that the beam will not break. Okay, so before we start, let's see what you would possibly need in order to solve this. There are two formulas we've looked at so far. One is for the normal stress, one is for the shear stress. I've written down both those formulas. Okay, so we are looking at a beam which is a rectangular cross section. Okay, and neutral axis clearly in the middle. We have also seen that the stresses, the normal stresses on a beam like this would be something like this. So there'll be a maximum stress at the edges, and it will be 0 right in the middle in the neutral axis. Now, if you do the same thing for the shear stress, like look at the stresses. Okay, so let me draw the same cross section, neutral axis. Okay, now here I would, well, there is a table which shows you how it varies. It's actually something I showed earlier. It is right here, right? This is the shear stress in a rectangular section. It's 3 divided by 2V divided by A. That's exactly in the middle. So I'm going to draw that here. So it will be like this. So tau max is 3 by 2 V divided by A. So I think you're given the P1B 3.59 in. You just need to compute D. Okay, so the key thing I want to emphasize here again, common mistake is the maximum stress occurs at the edge, at the outer edge. So maximum normal stress occurs at the outer edge, and of course the minimum too. And then the maximum shear stress occurs right in the middle. It's okay. We can simplify this. Is just make our life easy. We can actually compute the maximum stress. Y is what? D divided by 2, right? It's this D divided by the inertia is planar moment of inertia is BD cubed divided by 12. This comes from table A18. I showed it last time. It's in the notes. So sigma is simply 6m. I'm just simplifying this so that it'll make it easy to do the computations. And then tau is, well, it's can be simplified to, sorry, tau max is all we care about. This is sigma max, by the way. max, okay, tau max is 3 by 2 v divided by a. Okay, area is simply breadth times depth, BD. Okay, so we'll use these formulas a little bit later, but those are the formulas we'll require. Okay, so another thing to note is we also need V max and M max, right? We want to put max here because the point of failure is when the stresses are, or the moments are, well, the stresses are maximum, which means that the moments and the shear force are maximum. So in order to do that, we need to find the locations for V max and M max, which means that we need to draw a shear force bending moment diagram. So I will do that first. Okay, so first step, draw Vx and Mx curve to compute Vmax and Mmax, which are then needed for sigma and tau max. So in order to compute Vmax and sigma V and Mmax, we need to first draw the free body diagram. Okay, so here is the beam. Okay, so it's only going to have vertical forces. The horizontal forces essentially are not required. They all go to zero. So what VA, let's draw the dimensions first, 2, 3, and 2. 2, 3, 3, and 2. Unknown VA, unknown VP. Okay. Loads of 2.5 kip, 2.5, 1, and 2.5. Okay. So summation forces in the y direction should be 0. VA plus VB minus 2.5 minus 1 minus 2.5 equal to 0. So VA plus VB equals 6. Okay, then we can take moments about, I don't know, maybe about A. If you take moments about A, then 2.5 acts the distance of 2 meters from, or 2, I think it's 2 meters from A, and that creates a clockwise moment, negative. The force 1 acts the distance of 3 plus 2, 5, creates a clockwise moment. Then we have 2.5 acts the distance of 3 plus 3 plus 2, that's 8, and creates a clockwise moment. And then we have VB, which acts the distance of 2 plus 3 plus 3 plus 2, that's 10, and produces a counterclockwise moment, 0. Okay, from this, we can solve for VB. 5 plus 5 plus 8. No, 5 divided by 20, I think. It's 20. Uh, how would you get the values? So 3 and 3, yeah, it's probably 3 and 3. Yeah, you could solve it by symmetry. 3, that's what I get. So VA and VB are both 3. Oops. Okay, so that's the first part. We just computed VA and VB. Now we need to draw the shear force bending moment diagram. Without that, we cannot evaluate where the maximum shear force and bending moment will occur. Okay, so we'll just use the simpler method to do this, the graphical one. So just draw V as a function of X. Now we know this is 3. We know this is 3. Okay, so start from the left side. Initially, the shear force is 0, but then because of 3, it goes up. 3 stays 3 till we hit 2.5. So then it will be 3 minus 2.5, which will be 0.5. Stays at 0.5 till we hit the point where we have 1 Kipp's force acting downwards. So now will be 0.5 minus 1. So it'll go to minus 0.5. And it'll keep going till we hit 2.5 acting downwards. So then I'll have to do minus 2.5 minus 0.5 minus 3. And then keep going till we hit 3. And then the negative 3 and the positive 3 will give me 0. So that would be the shear force diagram. Okay, fairly straightforward. Let's do the bending moment diagram. Okay, so for the bending moment diagram, we just use the shear force diagram. It's much easier than trying to write equations for individual things. So we need the area, all these areas. Okay, so we can compute those areas. So this is going to be, height is 3, width is 2. So 3 times 2 is 6. For this one, we have 0.5 is height, and 3 is the width. So 1.5. This is clearly the same as that, with minus sign, and this one is the same as the top one with minus sign. Okay, so with that, we can draw the bending moment diagram. We'll start with 0, and we should have 6 at, let me draw this. We need this. Okay. Okay, so it starts at 0, goes all the way to 6 because the area is 6. And it's going to be linear because the shear force is constant, right? If the shear force is constant, the integral of a constant is a straight line. Then we have the next point is 1.5. So we have 6 plus 1.5 in straight line. This would be 6, 7.5. So I added 1.5 to 6. After that, we would have minus 1.5. So 7.5 minus 1.5 will go back to 6. And then we have 6 minus 6, so it'll go back to 0. This is 6, 7.5. Okay, I think now we are all set to think about this. So again, reminding you, sigma is 6m max divided by bd square, and tau max is 3v max. There. Yeah, 3 by 2 p times t. Okay, so where is m max? Clearly, the maximum m is here. $7.5. And where is Vmax? Vmax is, I think it's two places. One is here, and then another one is here. So that is, okay, so we will use those particular sections to do the calculation. Now there is one thing you have to be sure of, which is there are two criteria as mentioned here. If you look at the problem, there are two things. There are two stresses, sigma and tau. Okay. Let's say that we found that this point has Vmax, right? And then I think this point has Mmax. Okay, this will lead to tau max, and this will lead to sigma max. Okay, now what we need to do is this. We need to design it. So we don't know which is the critical point, if it's this one or this one. That is, in other words, let's say that we use this point to design for the D, right? We compute a D that's based on the maximum stress. We need to go back and check if the stress here at point, let me call that point C, the stress at C is actually less than the maximum possible. If it is less, then we are good to go. If it is not less than sigma max, it's greater than sigma max, that means our determination of the critical point, tau max, is incorrect, and we need to switch it. We need to design based on sigma max and then check if tau max is not met. So let me say that first before I start solving it here. So let's call this point how about we call this point as so anywhere here, in fact, anywhere here or here, the stress is maximum. So we could either of them is fine. So let's call that, let's just call that point, any point here as D. Okay, so D is one critical point, and then the other critical point is right at over here. So that critical point, let's call that C. Okay, so this is C is critical, and here D is critical. Okay, now here's what I just said, and I should probably put it forth here in words so that when you read it, it's clear to you. Okay. So the second piece is design for, I think it's D. Okay. So option one is this. Use sigma max at, I think it was point C, to compute D. Okay, D being the I think the height of the beam. Okay, once you do this, check if tau at D being the place where you D being the place where you have the critical stress is less than, I think I said, what's the maximum stress? It's 1800 and 120 psi. So use sigma equals 1800 psi at C to compute D and check if tau at D is less than 120 psi. Okay, if this is true, then you're good. If this checks out, D, which is obtained here, is good. If not, then you need to do the following. Go to B. So B is the following. Use tau equals 120 psi. Now, the maximum stress occurs at D to compute D. This is small d. Check if sigma at C, okay, the first point, is less than 1800 psi. If this checks out, D is good. Okay, so that's the pretty much the crux of it, and I illustrated this by following exactly this. So you will see that one of them will actually be violated, and one of them will be true. One of them will always be true.
Is there a possibility of them both true?
Then you'll choose the minimum of the two. Yeah. Both won't be true usually because you're trying to max it out.
True in the case that they're equal.
Yeah, they're equal. Yeah. Yeah, usually it will aren't be true. Yeah, right. Okay, so let's do A and then B. Okay, I think this is a good problem because it shows you the iterative nature of design. This is actually two steps, but more or less many times it's more than just one check. So let's do the step A. Okay, use sigma equal to 1800 psi at, I think it was D. At C, sorry. At C to design T. Okay, so this is as simple as taking this formula, sigma max equals, I think we wrote that down as 6 mBd square. Sigma max is 1800 psi. 6. Now M is 7.5, right? The maximum stress, M max. I need to actually convert that to, let's see what the units are. It's go back here. It's feet and kip feet. And then the units for this is psi, so it's in inches. So I need to convert it from kip feet to inches. So what I need to do is, so kip would be 10 raised to 3, and feet conversion would be 12. So this converts feet to inches, and this one converts kip to this is the kilo part in kip, psi. So the net result is psi. The K is what I'm converting for, divided by B, which is known. P is given as 3.5 inch. Okay, everything is in inch, so it's good. And then D square. So I need to solve only for D. So solve for D, you get 9.258 inch. Okay, this is my design based on sigma max. Now let's go back and check if this satisfies the maximum torque. Check if tau at, I think it was D, is less than 120 psi. Okay, we have a formula for tau. It is 3 divided by 2 v divided by b times d. Here we would put the max possible v. If you go back, you'll see that that max came from this figure. It's 3. 3 kip. Go back. 3 divided by 2. So I'll convert that kip to remove the kilo in kip. B is given as 3.5, and then D is something we computed, 9.5258. Okay, this comes from here. This is our design. Okay, so now if we compute tau, it comes out to be 138.8 psi. Okay, we have a problem. 138 psi is greater than 120 psi. Max allowed shear stress, right? Which means that this beam will fail in shear at C. If you use 9.258, if you choose D equals 9.258, the beam will fail in shear at D. So this is a bad design. It will not work. So we have to discard this design. Okay, so we go to the other option, probably the only option we have, which is we'll design based on the shear stress and then check if sigma condition is met. So the next part is reversing this idea of using sigma but using tau to design. So let's do that. This is the option B. We'll use tau Okay, so tau is max at I call that D, and 120 psi is the maximum. So use tau equal to 120 psi. That's the maximum possible shear stress at D to design the diameter. So that formula is tau equals 3 divided by 2 V max divided by B times D. So we'll choose the max value. So 120 is the max. V max, this is the shear stress at V, at D, so it's 3. So 3 kip, so I'll convert that to, convert that kilo to, convert that from kilos to, remove the kilos essentially, 3000 divided by B. B is 3.5 and the D is unknown. And so we can solve for D, comes out to be 10.714 inch. Okay, so we have a candidate D. We need to check if this D satisfies the stress at C. Check if sigma at C is less than 1800 psi. So let's go with this design. So sigma equals 6m max divided by BD square. So 6, the maximum moment is at D, and it is 7.5 kip feet. I need to convert that from kip, remove the kilo, and then feet to inches, so 12 divided by B, which is 3.5, and then there's a D, which is 10.714. Okay, now when I do this computation for sigma, I get 1344.07 psi, and this is actually less than 1800 psi. So since sigma is less than 1800 psi, this design is acceptable. So the answer to the problem is D equals 10.714. It's in inch. The final design. Okay, so it's kind of iterative here, but this is just 2 points. You could have other criteria. Yeah.
Sorry, go back to
This one.
yeah. Why would it be 3,000?
The actual force is 3. It's 3. No, there's difference. So this is the units of this is kip, and for this one it is kip foot. So the foot needs 12 to convert to inch. The kip is 1000.